Welcome to our first Sunday of the month global get-together. Tonight we have the special guest Jeremy Dunning-Davies with us via Skype, and tonight's event we're giving over to Rob, and this is going to be his little show, and I'm going to be talking to you, if you wish, through the Facebook group, and yeah, so we'll hand it over to Rob.
Hi, thanks, Phil. So first of all, thanks for watching. Welcome everybody. Special thanks to Jeremy Dunning-Davies, who's agreed to talk to us. For those of you that weren't at the Bath conference in the summer, Jeremy made a really interesting prediction concerning the work of Stephen Hawking in the summer, and it seems like in some way that prediction has been proven true. So we're going to ask Jeremy to talk to us about that in a minute. What Jeremy's talking about, will be talking about, is a kind of an instance or a particular example of a bigger problem, as we all know, faced by unorthodox theories, whether it was Berkeley with his currents, Halton Arc with intrinsic redshift, or what I'm going to be talking about today is another instance of this, which goes back into history. Michael Faraday is what some people call the father of electricity, and the trouble he had persuading people who were sold on a Newtonian cosmology. What he was talking about wasn't possible under Newtonian physics, so a lot of people tried to reject his work. So what we're talking about again is cosmology. An electric cosmology has a bit of a history, going back, I guess you could say, to Benjamin Franklin, who spoke about citizen scientists and using electricity as an egalitarian and democratic and empowering force. So our remit here is to talk about electronic cosmology, and specifically we'll be talking about how Michael Faraday's results contradicted the Newtonian, what became known as Newtonian cosmology, and the problems that caused him. To do that, we actually went and visited the Royal Institution, where Michael Faraday did most of his most famous work, including the discovery of electromagnetic induction. Going to the Royal Institution, we spoke to their professor of the history of science, a man called Frank James, and we had a really interesting chat with him, going to report on that. Also, just whilst we were there, I actually gave Frank James a little gift, a very simple little gift, and I'm going to show you that gift later on, and my prediction is that I'll never speak to Frank James again, because this gift, I think, slightly surprised him. But anyone wants to make predictions for what that little gift was, it wasn't expensive, but it freaked out the professor of the history of science at the Royal Institution, and it was really interesting, his reaction. I'll show you that later. But first of all, I want to turn to Jeremy Dunning-Davies and say thank you for being here, Jeremy. Would you please tell us first of all about the prediction you made in the Bath conference, and go on from there?
Well, thanks, Robert. Basically, at the Bath conference, I was talking about what had gone on in the history of not just physics, but other sciences, and how a lot has been hushed up and people have found difficulty pushing things forward. And I commented that a lot of people, scientists and others, for example, Thomas Kuhn, have suggested that you only get a major change in the course of science when some of the old school die off. Rather sad to say that, but this is a prediction that's been made. And I speculated in the summer that we might see a change in cosmology, astrophysics, sadly with the death of Stephen Hawking. Now, since that conference, I came back, and shortly after I'd returned home, I received a request to referee an article for a particular journal. Now, this was unusual in two ways. I haven't been asked to referee for journals for quite a while, but for this particular journal, the last contact I had with that journal before this communication was actually 30 years ago. It was in 1988, when I and a colleague sent up a letter to that journal. This letter was accepted for publication without any quibble whatsoever and appeared. So following the normal procedure with scientific publications, we then wrote the follow-up article detailing the theory behind what we said in the letter. This detailed article was rejected, and the journal would not back down on this, even when we said, well, if you don't publish this, surely you've got to publish something pointing out where our letter was wrong. But nothing happened at all. And to a large extent, myself and my colleague were blackballed from a lot of the frontline journals. Now, what did we actually predict in this, or what did we actually claim in this letter? Well, what we claimed in the letter was that the expression popularly known as the Bekenstein-Hawking expression for the entropy of a black hole was wrong. Simply that. Now, when I say popularly known, if you read the history in Hawking's book, A Brief History of Time, he tells you that this expression was actually derived by Jacob Bekenstein, and Hawking thought it was wrong and rejected it. But after 2 years pondering, he decided it was correct, and so it was accepted. And it then became known as the Bekenstein-Hawking entropy expression. This is the expression which he then refers to in his second book. I've forgotten the name of the second book now, but never mind. In his second book, he refers to the expression as what he would like put on his tombstone. In fact, I believe it is on his tombstone in Westminster Abbey.
It is.
The expression, of course, we said was wrong. The expression also was due to Bekenstein. Now, the interesting thing is that then, 30 years later, I'm asked to referee an article for this journal to do with black holes. In the referee's report, I commented that this entropy expression was wrong. I queried the whole theory of black holes, and the report was accepted, and the submitted article was in fact rejected on the basis of that report. If anybody wants to read the report, there's an organization known as Publons, P-U-B-L-O-N-S, and they publish these reports, and it's on their site. I'll be honest with you, I haven't checked it myself, but I know it's on their site. Subsequently, though, I was asked then to referee another article for that journal, which I did. I criticized the following article. It was on something totally different, actually, but my recommendations were accepted. It wasn't a rejection in this case. I recommended that there should be some, that the author should look again at certain claims they've made, and this was transmitted back to the authors. But this is what has happened, and it does make you wonder, is there some truth in this thought that there may, just may, be a change about to occur in astrophysics, cosmology, following the death of Stephen Hawking? I would say, Robert, that I did make this claim in Bath, or I put forward this thought, and I have to say it saddens me to do it.
You said so at the time.
It really does. Sorry?
I remember you saying so at the time.
Yes.
It was not a nice thing to have to say.
I hated saying it.
Yeah.
But I mean, I'll say it to you now, that I have the greatest admiration for Hawking the man, the way he put up with his affliction over all those years. But as a scientist, as far as I'm concerned, the jury is still out, because I'm still not completely sure, and I've asked others who feel the same, just what really major things he did achieve. I know there's the talk of the Hawking radiation, but this is a tricky one. It's a very neat little idea. But if black holes don't exist, then that's out of the window as well. And the idea of black holes is, I still feel, a very dubious idea.
Right.
If you look at forget about the electric universe for the moment, and if you look at the conventional way of looking at the life of a star, and you look at the theory which leads to the accepted theory which leads to the idea of a white dwarf, if you take that same theory and extend it to neutrons and get the idea of a neutron star, you can then go from a neutron star and go to an even smaller particle, a quark. You can find out what sort of properties a quark star would have. You can then look at what has been termed in the past subquarks and look at what properties a subquark star would have, and you find that with all these stars, just on a simple model, you find that the ratio of the mass to the radius gets closer and closer to that figure that is demanded for a black hole, but it doesn't achieve it. And so the idea is that if the conventional idea of the way in which stars end their lives is true, and that's an open question, but if it is true, it does seem that there's a hierarchy of states for which the end point may or may not be a black hole. But you see, with a black hole, it's a very peculiar thing because it all depends on a mathematical singularity. And I think most people, certainly myself, people I know, when we were first introduced to the idea of a singularity, we understood this was where the theory broke down. Mm. Now, if you look at that theory, you can go back to, look, I may not get the date exactly right, but it's something like 1784, when the Britisher Mitchell came up with the idea of, it's normally called a dark body, and Mitchell looked at the problem of finding the escape speed, finding the ratio of the mass to the radius of a body whose escape speed was equal to or greater than the speed of light. And this is just using Newtonian mechanics.
Yeah.
And you come up with exactly the same relation as they have for a black hole. So the idea of there being a body which has this value for the ratio of mass to radius is quite reasonable under Newtonian mechanics. But it isn't one of these black holes with all these extra properties. It's just a body whose escape speed is equal to or greater than the speed of light. And all that means is that this is the speed you need to get completely away from such a body. It would, in fact, be a body that you could see.
Right, so maybe the introduction of the singularity to that notional body was a way of getting around, or a way of allowing, because the singularity is, like you say, where the rules break down, essentially.
Yes.
So by introducing a singularity, you can say, well, look, this works now. By almost putting it as a fun
even
factor.
That's a bit dubious.
Yeah.
Even that's dubious because, look, I'm just talking now, so
yeah,
we're not putting sort of equations up, but everything is based on the Schwarzschild solution to Einstein's field equations.
Right.
And if you go back, if you look in all the books, any of the textbooks on general relativity and cosmology, you'll find this equation which is referred to as the Schwarzschild solution. But if you go back to Schwarzschild's actual paper, you find that his solution is not the solution that's appearing in all these books. His actual solution doesn't have this singularity. So I'm just left in a quandary.
Yeah.
What's it all about?
So by what mechanism would you say the singularity was appended to the Schwarzschild equation. I mean, how did that happen, do you think? Or why did that happen?
Well, I understand. The person to contact on this is a man called Stephen Crothers in Australia.
Yeah, Steve. Yeah.
Because Stephen has looked into this just tremendously.
Right.
And excuse me. Apparently, there was a modification made to the Schwarzschild solution by somebody. Stephen knows all the history of this. I don't.
Right. And
it's this modification which is appearing under Schwarzschild's name, but it is not Schwarzschild's solution. One of the problems here was that, of course, Schwarzschild's paper was in German, and people like myself and a lot of people in my generation don't understand German.
No.
But an Italian called Angelo Loinga actually translated Schwarzschild's original paper, and he published it on the archive site, the ARXIV site.
Yeah.
And I got a copy of Angelo's translation, and what I actually did was to get a copy of Schwarzschild's original article in the German and lay it alongside the translation, and literally, although I couldn't understand the German, I literally went through the maths line by line in both, and there is no doubt that Loinga's translation is valid. Some people may quibble with some of the translation of the German, I don't know, but the basic arguments are valid, and the solution that Schwarzschild came up with does not have the singularity that's causing this problem.
Okay, and does this relate? Thank you. Does this relate back to the Bekenstein equation and your? Because I'll be sorry, just be interested to hear what it was in broad terms about that equation that you were criticising back in 1988.
Well, the thing with the Bekenstein entropy expression is, you see, my background is more on thermodynamics, and my friend who used to be in Italy, Bernard Lavender, he was on thermodynamics as well, and we were looking at it from a thermodynamic point of view. And if you look at that expression, it actually, as it stands, it implies a violation of the second law of thermodynamics.
In that
it's got, it implies that there's a negative heat capacity in a closed system. And if you have a negative heat capacity in a closed system, you can devise a cycle that will violate the second law.
So what, matter or energy is being created?
So basically, you're getting something for nothing.
Right.
You're getting work done without expending energy, if you like.
Right.
I mean, the simple example or the simple way of looking at the second law really is to say that if it's violated, it means you can get something for nothing.
Yeah.
The crucial point again here is that in modern physics, a lot of people talk about the second law of thermodynamics by saying it tells you that entropy can never decrease.
Yes.
Well, number one, because no one's sure what entropy is, but number one, that statement is simply not true.
Go on.
And number two, if you're going to really look at the second law, you have to look at those forms of it that appeared at the beginning of thermodynamics. Those are the forms due to Lord Kelvin and due to Clausius.
Right.
And all they're concerned about is the operation of heat engines in cycles.
Yeah.
And so you must be talking about a cycle. Now, in a cycle, for a cyclic heat engine to actually operate, it will have one process in which entropy decreases, and that will be compensated by another leg of the cycle in which entropy increases, so that overall you don't get any change in entropy.
Right.
But you can have actual processes occurring in which entropy does decrease. So for somebody to say entropy never decreases, it's just not true.
Yes. Well, it's a as you say, as it's not a particularly well-defined term, or it's a very difficult term to define, and to relate everything to that term leaves you with a bit of a shaky foundation on which to measure things, doesn't it? I mean, if you can't really say what entropy is, to say that it cannot increase or decrease is
well,
then, isn't it?
When I say you can't say what it is, the problem with it is you can't easily say what it is physically. Some people talk about it being related to order and disorder, but that's a separate thing. Most people, when you talk about quantities that appear in thermodynamics, if you're talking about the volume of a body, most people have got a good idea what they mean by the volume of a body.
Yeah.
If you talk about the temperature of a body, well, look, it may be a hazy idea if you try to really pin it down philosophically, but everybody's got a good idea of what you mean by temperature. They've got a good idea of what you mean by hot and cold.
Yeah.
If you talk about energy, people have got a good idea. Pressure, you've got a good idea.
Yeah.
Heat, you've got a good idea. But entropy, now entropy, you see, it's easy for somebody with a mathematical background, it's easy for somebody to come up with the idea of entropy because you can use a mathematical argument in thermodynamics, which is quite mathematically straightforward, to show that a quantity appears and you know what its total differential is, to use a mathematical term.
Yeah.
And you just give it a name. So you've got this quantity, which is a change in a quantity, not the actual quantity itself.
Yeah.
And if you just work through the theory, it doesn't matter what it is. It's just a mathematical thing.
Yeah.
And that's the worry. Mathematics has brought something in, quite legitimately, but what is it physically?
Yeah.
And nobody really knows.
Yeah.
And this is one of the dangers with mathematics being so powerful,
And leading
not just in physics, but in science.
Yeah. So, I mean, to put it cutely, over the 30 years, has maths, between 1988 and this summer, has the maths changed? I mean, how is it that now what you were saying, which was, if you like, unorthodox or unacceptable, being obviously accepted or at least listened to by this magazine you're reviewing for? I mean, the maths has changed, or what, can you elaborate on that?
I'm sorry, Robert, I hate saying it, but as far as I am concerned, I can only think of one thing that has changed, and sadly, that is because someone has died.
And how does that operate? I mean, is it that people wouldn't want to associate with a paper that implied a criticism of Hawking? Is it? I mean, what mechanism do you see in play here that causes these things to happen? What's changed? Something changed in people's heads? Is something changed? Is there some smoke-filled room somewhere where they're going, oh, well, don't worry about it anymore? How do you see this, the mechanism of this change?
Well, look, let's be quite open and honest. What I'm going to say is pure speculation on my part.
Great, go for it.
But to me, for example, let me take another example. In 1992, a new journal came out called The Public Understanding of Science. And in it, an article appeared called The Hawking Phenomenon. And it was all about, it was basically about the book A Brief History of Time.
Right.
And I was annoyed by some things that occurred in that particular article.
Yeah.
And I wrote a very, very strong letter to the editor. I had a phone call back from them that they wanted to discuss something with me. And the points they wanted to discuss over this letter to the editor were trivial. I mean, one of them was simply, oh, we always publish the Christian name of authors. So are you willing to tell us your Christian name? I mean, literally, that was one of the questions. So this letter appeared And before it appeared, they had said to me that I appeared to be implying something or other at one point. And I said, yes, that's right. And they said, well, wouldn't it be better to put it down in black and white? So I said, well, if you're willing to print it, that's all right by me. So this letter to the editor appeared in 1993. Mm-hmm. There was never a single reaction to it. Nobody ever contacted me to agree with me or disagree. And I think this is one of the things that worries me, not just about this, but about a lot of things in science. I fear that if something is being pushed by a body that has, or a group that has some influence, if somebody writes something that is going to cause them real trouble, the best thing to do is keep quiet and ignore it. Don't respond, because if you don't respond, that article gets no publicity. Yeah. And so it will disappear.
You reminded me of the work of a linguist called John Marco Allegro, who was at the University of Manchester. He wrote something very controversial, and it was like radio's. After initial criticism, there was radio silence because they didn't want to give him the oxygen of publicity. So yeah, I think sometimes you're almost, if they criticise you, it's because they think they have grounds to do it. If they ignore you, it's because they know they can't make legitimate criticism, almost.
I think that is a reasonable conclusion to draw.
Yeah. So
I'm sorry to say it.
So imagine you were sending that article off today. It was 1988, because I'm hoping people who are watching and listening will be using what you know as a way of informing better practice in the future. If you knew then what you know now about, would you do anything different with the 1988 paper?
That's a good question, Robert, because...
Thank you.
No, I don't think I would, not in this instance, because, you see, I think you've got people, over my life, I've come across different types of people in universities. Mm-hmm. You've had people in universities who were passionately interested in their subject, and they did research in their subject purely because of that passion.
Yeah.
You've had people on the staff of universities who were passionately interested in their own preferment.
Yeah.
At any cost.
Careerists.
Yes, and that's all they're interested in. Mm. And they will, and you've probably got people in neither category as well. Yes. I mean, I think you've had people in the past, for example, who were genuinely more interested in teaching, or when they got into university, they became more interested in teaching than in research, and let the research slip, and just got on with the teaching. But it's the first two categories that I'm more concerned with, because I think that some of these people, I think if the career becomes over-important, or becomes all-important, then you could have people getting to the stage where they will do anything to protect their career, to protect their position.
Yeah.
And I fear that I'm not talking about physics here, I'm talking about generally in science.
Yeah.
It does worry me that could be the case.
Yeah. Well,
because if these people get to the position of authority, then they're ruling.
Yeah, well, yeah, it's often the problem with hierarchies, isn't it? The less adventurous stroke, the more conservative you are within that hierarchy, the more you're likely to rise up it. At the same time, you're more likely to entrench how that hierarchy is currently working, and therefore that mitigates against any progress.
Well, I couldn't agree more. Yes.
So, just as an observation, you've had this. You've quietly and with a certain amount of dignity stuck to your guns for the last 30 years. Do you feel in any way sort of vindicated by this? I mean, I think it's really interesting that it has almost, by definition, like you're saying about Thomas Kuhn and generational change. It's been like almost 30 years by the clock, 30 years almost exactly is one generation.
Yeah.
Do you feel vindicated by that, or how do you feel?
Do you know, Robert, in many ways, I'm not sure that I feel anything. You see, I think I've been naive in my life, because when I was still on university staff, if I looked into a problem, I looked into it for one reason, because it was an academic problem that interested me at that time.
Yeah.
I honestly didn't look into them for any other reason. And I always felt that I'd come up with the correct solution. Occasionally I didn't, and I was quite happy to admit, no, I've got a mistake there, or this could be extended or something. But because I was doing it from that point of view, I'm not sure that I felt anything, except maybe when I had that request to referee the article, there was a little bit of curiosity, because my initial reaction was, oh, I don't want to bother to referee articles again. And then I thought, given that it's that journal, I'm curious why after 30 years. And it was simply that.
It's a really interesting...
I don't know if that's a fair answer.
I just think it's a really interesting real-world instance. I saw you make that prediction in Bath. Here we are talking about it. It's a really interesting instance of that general pattern that Thomas Kuhn wrote a book about, and other people, I'm sure, within the electric cosmology or electric universe community, people will be experiencing that in their own ways all the time. Whether it's submitting academic journals or even just having conversations with friends and colleagues when trying to help people or move people's paradigms on. It occurs not just in science, it occurs in religious reformation, anything you want to, any human activity almost. And it's just your prediction and then this vindication, or the fact you've been asked to do this refereeing, I just think it's a really interesting instance of that. So thank you for sharing, because honestly...
I'll just say one thing, Robert.
Please.
If I may.
Of course.
Over something like, for example, black holes.
Yeah.
I think it is quite reasonable for anybody to turn around and say, oh, well, what does it matter?
Yeah.
And I would say to them, I say, well, I can see your point. But what does matter is that if this attitude is pervading astrophysics cosmology, it means that it is definitely pervading other areas of science.
Definitely.
And that means it's pervading medicine.
Yeah.
And that people's lives are directly affected.
Yeah.
And that, I think it's that thought that is the thing that worries me most about this business associated with black holes.
Sure. I mean, again, like if you take a step back from science, you can see it playing out in all kinds of ways around the world today. This kind of rigidity of thinking, this lack of adaptivity, has all kinds of human consequences, especially for, the electric universe theory. I thought your experience was just sort of, paradigmatic, or, a really good example of the kind of problems people face every day. And I think the way you talk about it with such equanimity and it is really, really awesome, because some people after 30 years might be angry about it. You haven't exercised that at all, and it's kind of inspiring to see, because some of us are starting out on things now that maybe in 30 years' time we'll be able to look back on, and it's to see your example. I think is basically thank you for sharing. Your
well, it's lovely of you to say so, Robert. But there's no point in being angry. It's not going to get you anywhere.
Well, there's wisdom as well as knowledge there, sir. So that's awesome.
Well, thank you.
No, thank you. Now, if you don't mind, I was going to talk a little bit about, because following on from talking to you and how your experience has, what your experience has been, I wanted to talk a little bit about Michael Faraday and the experiences he had, like nearly 200 years ago. Because another instance of this general problem that we've come across. And from my point of view, the way that Newton was put on a pedestal is similar. Obviously, Newton's a bigger figure, but similar to the way that Hawking has in our kind of, in the last few years. Hawking is in that kind of almost untouchable position of being almost
put in the untouchable position.
Yeah.
But I honestly don't think that anybody should put him alongside Newton.
No.
I mean, Newton did a lot of things that were not very nice.
Yes.
And
we're going to talk about a couple of them.
the way he got rid of most references to Hooke, for example.
Yeah, Robert.
But he did a tremendous amount, which has stood the test of time.
Absolutely.
And
it's more what I think. Well, what I was going to talk about was more how people adopted Newton's name, and things became Newtonian, if you like, that weren't strictly from Newton. Specifically, the theory of the atom that goes all the way back to Democritus, as you know. But if you, because what we did was I went to the Royal Institution and spoke to Professor Frank James of the Royal Institution, their Professor of the History of Science. And Phil, if you don't mind, could you just stick up? We're going to just show a little bit of footage of Frank just to show people who he is. It's like 10 seconds. Here he is. This is Frank James.
The Times on the 17th of December 1825 carried this advert advertising the first Christmas lecture to be held during the 1825-26 season.
Okay, you can probably pause it there, Phil.
It declared a course of lectures to be delivered at the Royal Institution in the Christmas and other vacations on some of the leading branches of natural philosophy adapted to the comprehension of the juvenile auditory.
So that's just to show people who Frank James is. He's introducing the idea of the Christmas lectures there. In the run-up to meeting him, I read a couple of his books. One was a short introduction of Michael Faraday, and for those who don't know, I was just going to quickly run through Faraday's biography, because Michael Faraday was born in South London, the son of a blacksmith. He was born the son of a blacksmith. He saw his father's work take a very heavy toll on him, and he was determined to try and get out of physical work. When he was 13, he became a bookbinder, and apparently there gained his interest in reading science books especially. His enthusiasm for science eventually led to him being given a couple of tickets by someone who shared his interest in science, given a couple of tickets to see a guy called Humphrey Davy, who was a bit like the star scientist of the day, of the early 19th century. He went to see Davy's lecture and made notes on it. He then wrote those notes out and turned them into a book. He bound them into a book, which he gave to Davy. Davy accepted this very generous and slightly sycophantic offering, and later on invited Faraday to become Davy's assistant in the lab. Faraday jumped into that opportunity with both feet, and slowly rose up the ranks of the Royal Institution. Interestingly, at one point, Humphrey Davy tried to stop Faraday becoming, I think, a fellow of the Royal Society. He thought, because he wasn't a gentleman as such, because he had to work for a living, Davy felt he wasn't appropriate. But that's a rough biography of Faraday. Faraday's famous for discovering electromagnetic conduction. He also discovered, I think, and certainly did work on the benzene ring, and he was generally interested in demonstrating the unity of the electric force. It's kind of a rerun of Volta versus Galvani, with Faraday being a bit like Volta and saying that there's only really one sort of type of electricity. The book that the other book apart from the biography I read was The Chemical History of a Candle by Michael Faraday, and I just wanted to read from that because this was a bestseller in the day, and I think it's still one of the best-selling science books of all time, better selling even than A Brief History of Time. In The Chemical History of a Candle, Faraday says, "There is not a law which any part of this universe is governed, which does not come into play and is touched upon in these phenomena. There is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle. So he was saying back then, even any candle you want is the best possible introduction into the world of physics and natural philosophy. It's a very nice egalitarian idea, because it means you don't need £1 million of equipment. You need a candle and your God-given kind of intelligence. And that was, I think, part of the popularity of his talk, because he was allowing people to see into this phenomena that they're all familiar with in much more depth. In the chemical history of the candle, he talks about the flame, he talks about its structure, how the differences in brightnesses, how air is consumed, how water is produced, hydrogen, the other part of water, he called it the other part of water, other than hydrogen, oxygen, carbonic acid, which is we call CO2, and carbon. And he was showing that everything was connected with everything else, even if you couldn't necessarily see the connections. Electromagnetic induction is what he's famous for. Can you tee up the next little vid? There we go. So this is just an example, a demonstration of electromagnetic
Michael
induction.
Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing.
I think that'll do, Phil. Okay.
And now let me connect the 100 loop coil.
So that's just an example or a demonstration of electromagnetic induction, which caused all kinds of philosophical problems for people, because you could see the magnet and the coil were not touching, and yet they were affecting each other. And this leads into some of the more controversial things Faraday said about lines of force and things being able to affect each other at a distance. You can see there that the number of coils of wire, of copper, the number of turns on the copper coil is an important factor. We're going to come back to that later on when we're talking about the work of Eric Lathwaite. So having demonstrated induction in 1832, Faraday went on to show that voltaic, magnetic, thermo and animal electricities, all different labels for different electricities at the time, all related to the same phenomena. So he showed that the unity of the electromagnetic phenomena, which of course was sort of confirmed mathematically by James Clerk Maxwell later. So you have Faraday showing these results and doing these experiments. He came across resistance from what I'm going to broadly call Newtonian thinkers. Now, Newtonian's not Newton. Newton himself we're going to talk about in a minute, but Newtonians were people who associated themselves with Newton and possibly used his status to lend credence to their own opinions. Now, first thing we need to say about the Newtonian cosmology is that basically space is a vacuum, and that vacuum is populated by individual ball-bearing-like particles, whether they be protons, neutrons, whatever, atoms. So we've got this atoms in a vacuum. And can you, Phil, this actually goes back to the work of the theories Democritus, who was a Greek from about 250, 300 BC, and he said, nothing exists except atoms and empty space.
HP InfoSight makes our storage the only storage smart enough to predict and prevent 86% of issues.
So we've got an advert, hang on.
Yeah, I had it set up, but of course I have to put it in as soon as you go and do it.
Yeah. So this is just about the history of the atom.
More than 2,000 years ago, the Greek philosopher Democritus stated that matter could not be divided into smaller and smaller pieces forever. Eventually, the smallest piece of matter could be obtained. This idea was largely forgotten until the early 1800s. That's when English chemist John Dalton began observing the activities of weather by studying gases. Through his experiments and observations, Dalton developed the basic ideas of the atomic theory. Dalton concluded that pure substances, called elements, are made of extremely small particles called atoms. He stated that atoms of the same element are exactly alike, and the atoms of different elements are different from one another. Dalton also stated that atoms could not be changed into different types of atoms by chemical reactions. He also theorized that compounds are formed by joining the atoms of two or more elements. These ideas served as the basis for what is known as the atomic theory.
Okay, thanks. So there's atomic theory. It was very much a very popular theory with, say, Robert Boyle and the whole Royal Society set this idea that you have a vacuum of space and it's a series of corpuscles or atoms or bits of matter, clumps of matter bashing into each other. So that actually predates Newton, but is very much part of the Newtonian outlook. Can we have a look at the three laws of motion now, please? This is obviously part of what Newton was famous
Physicist
for.
and philosopher Sir Isaac Newton revolutionized the world's understanding of the physical universe with his three laws of motion. Newton's first law of motion states that all objects continue in a state of rest or uniform speed in a straight line unless acted upon by a non-zero net force. In other words, an object at rest tends to stay at rest, and an object in motion tends to stay in motion, unless acted upon by an outside force. This law can be observed when a tablecloth is whipped from underneath a dinner setting while the dishes remain in place. Because the dishes were initially at rest, they will continue in their state of rest. Likewise, when a fast-moving subway car comes to a quick stop, passengers inside continue traveling at the previous uniform speed of the car and get thrown forward. This property of matter to remain at rest or in motion is known as inertia. Newton's first law is often termed the law of inertia. Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. This basically means that it takes a greater force to move or accelerate objects with greater mass than it does objects with lesser mass. Mathematically stated, a moving object's acceleration equals the net force acting upon the object divided by the mass of the object, or A equals F divided by M, where acceleration is measured in meters per second squared, force is measured in newtons, and mass is measured in kilograms. This equation dictates that acceleration is directly proportional to force and inversely proportional to mass. When force increases, acceleration increases. And when mass increases, acceleration decreases. Take, for instance, a scenario where you're pushing a 10-kilogram box along the ground with a force of 20 newtons. The acceleration of the box equals the force you exert, divided by the mass of the box, or 2 meters per second squared. If you push 10 newtons harder, the acceleration of the box will increase in direct proportion and becomes 3 meters per second squared. If the mass of the box is increased to 20, but the force stays the same, the acceleration will decrease in inverse proportion to 1 meter per second squared. Newton's third law of motion states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. In other words, when one object pushes against another, the force applied by the first object is opposed by the force of the second object that is equal in magnitude, but in the opposite direction. For every action, there is an equal and opposite reaction. These equal but opposite action-reaction pairs define...
So that was taking us back to high school, I guess, in terms of our physics. Reason for showing that is to underline how simple and universal Newton's laws were and quite what a powerful effect they had. It's true to say that 1642, he was born on Christmas Day, 1642. Many people in the Royal Society thought that we should scrap the birthday of Jesus Christ as a millennial marker and go with the birthday of Isaac Newton. They were people who talked about 1642 being year one Anno Newton, and they actually put him on that kind of pedestal. His work was very, very, very powerful. I mean, we've got these atoms, all of them for all time are subject to these three sets of rules. That means, in theory, you can start working out. If you had a big enough calculator or big enough computer, let's say, you could work out the trajectories of every atom in the universe and predict with complete certainty where everything would be. His laws of motion made people think that the world was deterministic, and a deterministic mechanism that you could predict with almost complete certainty. So the third law especially, I think, is interesting because every action has an equal and opposite reaction. It's kind of a mathematical way of expressing the golden rule, which is do unto others as you have them do unto yourselves. Again, Newton was viewed as a kind of almost mathematical messiah or some kind of mathematical lawgiver like Moses. He was put on a pedestal, obviously because of the incredible insight and power of his work, and then later he became more and more of a myth and less of the man he really was. Newton was very different from the public image, and he's sort of canonised as the embodiment of reason. But Germany already mentioned Robert Hooke and the interactions they had. Might as well mention that now. Actually, can we play the next clip?
Okay.
This will give you an insight into the type of person Newton really was. Yes, mate.
Decidedly odd figure, brilliant beyond measure, but solitary, joyless, prickly to the point of paranoia, famously distracted. Upon swinging his feet out of bed in the morning, he would reportedly sometimes sit for hours, immobilized by the sudden rush of thoughts to his head, and capable of the most riveting strangeness. He built his own laboratory, the first at Cambridge, but then engaged in the most bizarre experiments. Once he inserted a bodkin, a long needle of the sort used for sewing leather, into his eye socket and rubbed it around, betwixt my eye and the bone, as near to the back side of my eye as I could, just to see what would happen. What happened, miraculously, was nothing, at least nothing lasting. On another occasion, he stared at the sun for as long as he could bear, to determine what effect it would have upon his vision. Again, he escaped lasting damage, though he had to spend some days in a darkened room before his eyes forgave him. Set atop these odd beliefs and quirky traits, however, was the mind of a supreme genius, though even when working in conventional channels, he often showed a tendency to peculiarity. As a student, frustrated by the limitations of conventional mathematics, he invented an entirely new form, the calculus, but then told no one about it for 27 years. In like manner, he did work in optics that transformed our understanding of light and laid the foundation for the science of spectroscopy, and again chose not to share the results for 3 decades. For all his brilliance, real science accounted for only a part of his interests. At least half his working life was given over to alchemy and wayward religious pursuits. These were not mere dabblings, but wholehearted devotions. He was a secret adherent of a dangerously heretical sect called Arianism, whose principal tenet was the belief that there had been no Holy Trinity, slightly ironic since Newton's College at Cambridge was Trinity. He spent endless hours studying the floor plan of the lost temple of King Solomon in Jerusalem, teaching himself Hebrew in the process, the better to scan original texts, in the belief that it held mathematical clues to the dates of the second coming of Christ and the end of the world.
Okay.
His attack.
So, thank you. You can, from that, I hope you get a flavour of the kind of person Newton apparently was if you read a real biography of him. Insular, tetchy, didn't go out much. He's not known to have had any lovers of any kind. He didn't really have many friends, maybe one or two people he bonded with throughout his life, and he cut a strange figure. He's usually credited with the creation of the inverse square law, and here we go on about Robert Hooke, as Jeremy mentioned earlier. Robert Hooke, the curator of experiments at the Royal Society, was the person who's first on record as suggesting the inverse square law as being the mechanics of gravitation. Now, Edmund Halley of Halley's Comet took Robert Hooke's idea to Cambridge and talked to this very prickly man called Isaac Newton, that everyone knew was a mathematical genius. Now, Newton, Halley said, well, what do you think about this idea of the inverse proportion of gravitation? And Newton said, yeah, that's definitely true. Halley said, well, wouldn't that give rise to elliptical orbits? And again, Newton said, yeah, that's true, and I've proven it. So he actually said, oh, yeah, I've proven it. Halley said, oh, can I see the proof? And then Newton rummaged around for 10 minutes, maybe an hour, I don't know, saying he'd lost the papers that proved that the inverse square law would result in elliptical orbits. Now, later on, Robert Hooke and Isaac Newton had a dispute about who originated this idea. The record shows that it was Hooke. There's no real argument about that. There's apparently records in the Royal Society. But when Newton became president of the Royal Society, he had all records, or all mentions, I think, of Robert Hooke taken out of the Royal Society notes, and he had all the portraits of him burnt. Very famously, a woman called Lisa Jardine wrote a brilliant biography of Robert Hooke and actually found a portrait of him that somehow got squirreled away. But Isaac Newton was not this cold, dispassionate, calculating man. He was a man who was obsessed, spent as much time looking at the Bible as he did at physics, was obsessed with the Temple of Solomon in that kind of Masonic way, was obsessed by the return of the Second Coming and stuff. But like, as time went on, he got put more and more onto a pedestal, and his actual human nature, if you like, was ignored in favour of his this image of him as being some kind of ultimate, calculating, dispassionate scientist. The Newtonian universe is kind of a calculable place. It's mathematically predictable, and it kind of led to what we now call, or this kind of thinking led to what we now call a uniformitarianism, in that small changes over long periods of time were what really made the universe tick. The universe was predictable mathematically, but because of Newton's three laws, if you had a big enough computer, you could work out where every atom was and what it's going to do for the rest of the time. This way of looking at things, this Newtonianism, had its critics, and the best example, I think, of a short critique of this came from a man called Jonathan Swift. If you imagine you've got your hands full of Scrabble pieces, he said that the universe was formed by the fortuitous concourse of atoms. I will no more believe than that the accidental jumbling of the alphabet would fall into the most ingenious treatise of philosophy. I.e., if you throw all the Scrabble pieces up in the air, what are the chances that you get something really clever happen at random? The chances are very, very small, and this was Swift's point. And even back in the early 18th century, saying that this idea of a mechanical universe with things just happening at random just didn't really seem to make sense. So the Newtonians, not necessarily Newton, but the Newtonians had this uniformitarian kind of evolution of slow, random changes over vast amounts of time. And this is what I'd call a fairly cold and cold-hearted cosmology, purely mechanical, purely deterministic. Faraday was not a fan of this. This is a brilliant quote from the candle. We are made, Faraday said, dependent not merely on our fellow creatures, but on our fellow existers, all nature being tied together by laws that make one part conduce to the good of another. So I'll say that again. All nature's made so every part helps every other part. One part is conducive to the good of another. This is Faraday's cosmology. Everything working together, connected, not just random billiard balls bashing into each other. This is a kinder cosmology, a less cold, mechanistic one. And it's, according to Frank James, the language that Faraday used in the Chemical History of the Candle was deliberately theological. There's a quote, a review of from Church Monthly about the book, The Chemical History of the Candle, where they said, God's power and love are shown in a little and common thing. The style is a model for those that try to interest children in the grander mysteries of faith and the holy duty of things. So, in some ways, Faraday's lectures and the Christmas lectures were almost theological in nature. He was trying to get across more than just individual facts. He was trying to get across a worldview that was very different to the Newtonian one. So his experiment showed that this billions of billiard balls bashing into each other did not account for all the things that he found experimentally. And he drew some conclusions about that, which were elaborated on by A.P. David at one of the Thunderbolts conferences. And if you would, Phil, the next bit of film is A.P. David talking about Faraday's view of the atom. Thanks.
Or both, or neither. If we must assume it all, as indeed in a branch of knowledge like the present, let me show you this one. This is the usual picture of atoms at that time, anyway, a nucleus and space. If we must assume it all as indeed in a branch of knowledge like the present, we can hardly help it, then the safest course appears to be to assume as little as possible. And in that respect, the Boscovich atom, the atoms of Boscovich appear to me to have a great advantage. The Boscovich atoms are mere centers of force or powers, not particles of matter in which the powers themselves reside. If in the ordinary view of atoms, we call the particle of matter away from the powers A, and the system of powers or forces in and around it M, then in Boscovich's theory, A disappears, or is a mere mathematical point, whilst in the usual notion, it is a little unchangeable, impenetrable piece of matter, and M is an atmosphere of force grouped around it. How can we for a moment imagine that potassium's conducting property belongs to it any otherwise than a consequence of the properties of the space, or as I have called it above, the M? So also its other properties in regard to light or magnetism or solidity or hardness or specific gravity must belong to it in consequence of the properties or forces of the M, not those of the A, which, without the forces, is conceived of as having no powers. But then surely the M is the matter of the potassium. To my mind, therefore, the A or nucleus vanishes and the substance consists of the powers, or M. Hence, matter will be continuous throughout, and in considering a mass of it, we have not to suppose a distinction between its atoms in any intervening space. The powers around the centers give these centers the properties of atoms of matter. In such a view, all the contradiction resulting from the consideration of electric insulation and conduction disappears. The atoms may be conceived of as highly elastic. If an atom be conceived to be a center of power, that which is ordinarily referred to under the term shape would now be referred to the disposition and relative intensity of the forces. Now, to be sure, Faraday is doing plenty of assuming and speculating here, but there is a method to the metaphysics. In order for the phenomena to play out on the stage in the way we observe them to do, in this case the insulating and conducting properties of different materials, what must be going on behind the scenes? Given that we have independent evidence from chemistry that matter is in measurable ways an atomic phenomenon, what properties do these invisible atoms need to have? We are all, in fact, quite used to dealing with this, and the activity is no less metaphysical for our being used to it, nor is it any less metaphysical for being highly pragmatic. We have a way of assuming, only what needs to be there to be consistent with the results. It's a sort of need-to-know basis. Let's just go with that, with what works, right? You'll be familiar with the Bohr atom. It's very useful. It models valence, it allows you to picture quantum jumps, and so on. But it is a bit of orbital metaphysics that we know by independent means cannot reflect the reality. Yet it is all the same, fit for purpose, and more than a little elegant. Less eloquent, but equally fit for purpose, is this diagram from an EE textbook, courtesy of my wife's bookshelf. You've got your insulator, your semiconductor, and your conductor, your valence and conduction bands. This is a schematic fit for purpose, which, like all models, is purely metaphysical. So Faraday's reasoning and the Boscovich atom can take their place alongside these, if they also are fit for purpose. Here I let the great experimentalist finish his train of thought. As regards the mutual penetrability of matter, one would think that the facts respecting potassium and its compounds already described will be enough to prove that point to a mind which accepts a fact for a fact, and is not obstructed in its judgment by preconceived notions. With respect to the penetrability of the atoms, it seems to me to present in many points of view a more beautiful, yet equally probable and philosophic idea of the constitution of bodies than the other hypotheses, especially in the case of chemical combination. If we suppose an atom of oxygen and an atom of potassium about to combine and produce potash, I guess this is potassium hydrate, hydroxide. The hypothesis of solid, unchangeable, impenetrable atoms places these two particles side by side in a position easily because mechanically imagined and not unfrequently represented. Think of the Bohr atoms. But if these two atoms be centers of power, they will mutually penetrate to the very centers, thus forming one atom or molecule with powers either uniformly around it or arranged as the resultant of the powers of the two constituent forms. And the manner in which two or many centers of force may in this way combine, and afterwards under the dominion of stronger forces separate again, may in some degree be illustrated by the beautiful case of the conjunction of two sea waves of different velocities into one, their perfect union for a time, and final separation into the constituent waves. Yes, I say, Mr. Faraday, beautiful indeed. And that is not nothing when it comes to the persuasive power of natural philosophy. This beauty is not the jam on the toast. In his conclusion, he returns our own thought to that final paragraph from Newton's Principia. Again, this is Faraday. The view now stated in the constitution of matter would seem to involve necessarily the conclusion that matter fills all space, or at least all space to which gravitation extends, including the sun and its system. For gravitation is a property of matter dependent on a certain force, and it is this force which constitutes the matter. In that view, matter is not merely mutually penetrable, but each atom extends, so to say, throughout the whole of the solar system, yet always retaining its own center of force. This at first sight seems to fall in very harmoniously with Mossotti's mathematical investigations and reference of the phenomena of electricity, cohesion, gravitation, and so on to one force in matter. And also again with the old adage, matter cannot act where it is not. Now, I want you to note how definitively the tables have been turned on Newton. The subtle spirit has done much more than penetrate the impenetrable solidity of gravitating matter. It has exploded the stuff from within. Faraday's consideration of conduction, insulation, and other facts having to do with chemical reactions and volume have led to a view of the fact of gravity which is no longer compatible with the theory that its force is proportional to the density of matter. Faraday's own preferred metaphysical underpinning, the Boscovich atom, now conceived as a field of force whose center offers nothing more than a location, does not cohere with any simple notion of density. I believe there is nascent here a tenet of electric universe theory. To his own required metaphysics, I will finally turn.
Thank you, Phil. Thanks. Good. Pause it. Can we pause it?
Who's going to?
Well done. He went quiet there, sorry. Yeah. Thanks for the small clap. So right. What you're actually seeing there is obviously AP David talking in 2015. But the point is what Faraday was saying, I don't know if you saw the difference between the Boscovich atom and let's call it the Newtonian atom. There was nothing solid in the middle of that atom. In other words, I mean, this is something Professor James confirmed because I was curious. Faraday said there was no such thing as the material. All there were forces. So, as AP David noted, this is a 180-degree turn on Newtonian physics. And it's really worth recalling that the person they call the father of electromagnetism thought matter was an epiphenomenon, thought matter was something we experience as a matter of consequence to the reality which is just forces. I mean, another thing Faraday is famous is saying he thought gravity was nothing but a side phenomenon of electromagnetism. He put everything under the umbrella of electricity. It's something I think everyone in the electric universe community would agree with. And he stated categorically back then he thought gravity was just a side phenomenon of the broader electronic phenomenon. And again, you don't really get to hear that so much anymore. Faraday is talked about, but his cosmology, this fact, the way he viewed things, is not addressed, I'm going to say. Now, again, Professor James talked to him about this, and if you remember, I gave Professor Frank James something that's almost certainly going to mean I never talk to him again, and I'm just going to remind you of that because I'm going to show you that in a minute. But he was talking about Faraday as an establishment figure, and he kept on in that train. I kept on asking about the controversies that Faraday experienced. He underplayed them. He said that I've been down to the museum in the Royal Institution. The museum's okay, not very exciting. You see a lot of the original equipment that Faraday used, which is nearly 200 years old, on shelves. That's pretty much it. It's true to say at the time, though, some of Faraday's theories were vehemently opposed, because they did oppose, and 180 degrees different from the kind of uniformitarianism, mechanistic determinism that Newtonians believed in. They again believed that everything was mechanical and predictable mathematically. What Faraday was showing was that there's more to life than atoms. Sorry, Phil. Yeah.
Yeah, I was just saying, can we just sort of ask Jeremy, what do you think of the atom? Do you think it's vortex of energy, or do you think it's solid matter? Do you go with the Boscovich version of what an atom is? What do you think, Jeremy?
I don't really know the answer to that one. I would comment on just one thing, if I may, though. I'd like to correct something that came up earlier about Newton's three laws.
Yeah.
The second law, as put forward in the presentation, was only true if the mass is held constant.
Right.
The actual statement of Newton's second law is that the force is proportional to the rate of change of the momentum. So it's only equal to mass times acceleration if the mass is a constant. So we've got to be very careful on that one, because we have a lot of systems where the mass isn't a constant, and that form of the second law doesn't actually hold. But as for the question you've just posed, I don't know the answer. But what I do know is that in the 1800s, people were concentrating on research in electromagnetism. They were desperately searching for an explanation of mass in terms of electromagnetic ideas.
Yeah, well, we now seem to sort of think that mass actually alters with the amount of charge it has, as shown by comets, and why they thought they was grubby snowballs in the first place.
Yeah.
So we are going back to the factors. Where is it discharge or is it charge or matter? Yeah, it's a hard one to actually come to a determined idea on, really.
I think it's very difficult, but I think it does illustrate, if they're coming around to that idea, it does illustrate that with the coming of relativity and the forcing of gravity into the foreground of science at the expense of electromagnetism, science has possibly wasted 100 years.
Yeah, I think we all agree with that. I mean, we're taken down the wrong road. Purely, it seems like for financial and political reasons, and we have wasted 100 years. All the advancements we've had in the 20th century have been electromagnetic, misunderstanding and powering our electricity. Anyway, let's get back to
I was going to say, I remember you saying, Jeremy, when Phil and I came and spoke, see you speak in Charing Cross, and you said something along the lines of post Tesla, maybe what Tesla was able to engineer was so shocking, I'm going to say, or potentially powerful, some kind of information management became necessary because otherwise people were going to become overly empowered. And I just wanted to say, I thought it was really interesting that Tesla said there was no such thing as an electron as an experimentalist, and Faraday said there was no such thing in that, according to that, there's no such thing as a nucleus. So according to two great experimentalists, we haven't got a nucleus and we haven't got an electron, which I think is quite an interesting...
well, we got them, but they're not as solid particles. They're as energy expressions, right. Which I go along with the electron. I'm not sure about the nucleus.
They're two engineers. Engineers are the people who... I just think those are two interesting
Well, I certainly go more with an engineer than I would with
mathematical theorists.
Yes, absolutely.
But I think you've got to. I mean, you hear mentioned two extreme experimentalists and people who thought deeply about things. And you see, as far as the electric universe, for example, is concerned, you're going back to Christian Birkeland. And if you think about Birkeland and his history, which was all to do with observation and experiment, and yet his ideas were ignored in favour of a mathematical theory, a purely mathematical theory, due to Chapman. I mean, it's where are we? Mathematics is important, and I would stress that. I firmly believe that, but it is important as a tool in physics.
It's also
not there as the primary method of examining.
No, it's a way of going on from something. But you need that original concept to be strong from observation and experiment, and then use the maths to expand from that. You can't just guess and express it in maths. I mean, you might as well write a book, because it's either going to be fiction or it's going to be reality. So you've got to start because maths is a language,
Yes.
That's it. And but you've got to start from the experimental first, surely.
I think
it's a language to express, to put down on paper a theory which is based on experiment.
Yeah.
But it's not there to start off the thing. It's the experiment and the observation that must be the starting point.
Absolutely.
Yeah. I can't. Whenever someone says something like maths is the language of nature, I ask them then, what about pi? I mean, if a circle is such a natural thing, if maths was equally natural, why is pi such a complicated infinite regress? You can also go on about the square root of the square root of 1. What is it? Square root of 1. These things tend to prove that maths, whilst a very beautiful and beautiful thing, isn't the language of nature. To say so is to go a bit beyond. Well,
I think one of the dangers, Robert, is that people get wrapped up in the beauty of some mathematics. I did so myself. As an undergraduate, my favourite subject definitely was relativity, both special and general. But why did I like it? I was doing a maths degree and I loved the mathematics of it. When you start to really think about it and put the physics in, you then start to get a different perspective on things. So you've got to be very, very careful about the beauty of mathematics in isolation.
Yeah, people become sort of intoxicated on by it, and forget about what it's based on. If I may, I'm going to just, because we've talked about now a couple of sort of more engineering based scientists in Faraday. And I've forgotten who the other one was. But when I was talking to, when I went to meet Professor James at the Royal Institute, he wanted to sort of know why I was there, and he asked a couple of questions about perpetual motion to see if that was why I was asking about Faraday and so on and so forth. Eventually, he seemed to be satisfied that I wasn't some kind of nutcase with a particular axe to grind. So at that point, something really interesting happened, which I wanted to share. I've mentioned in my emails to him about Eric Laithwaite and how I was a fan of Laithwaite's Christmas lectures. And having spoken to Frank over a cup of coffee for about 20 minutes, half an hour, he suddenly just opened up and offered this apology to me on behalf of the Royal Institution about how terrible it was how Eric Laithwaite had been treated. And again, it's interesting, you got, like we say, Faraday and Tesla, not particularly popular people amongst the theoreticians. Eric Laithwaite, was an incredible engineer and became incredibly unpopular amongst theoreticians. And there's some really, really interesting stuff there. I mean, again, going back to inductance and the number of coils, if you don't mind, Phil, we'll look at the next clip. And this is Eric Laithwaite talking about spin in mass. And this is the kind of thinking that in the 20th century got him into serious trouble.
Okay.
Thanks.
Cool that one down.
This is part of Eric Laithwaite's Christmas lecture in 1974 or 5, I think. Look what he has to say.
Are these discoveries new? Well, not entirely. I've had letters from all kinds of people who've done similar experiments before, and for one reason or another have given up for 1, lack of know-how and scientific background, 2, lack of money and workshop facilities, 3, lack of courage, 4, lack of anyone to listen, especially 4. Now today I've got all of you here ready to listen. What a pleasure it is to talk to young people who are ready to listen after you've talked to adults. Quite the most amazing letter I had was from a man who wrote quite unemotionally that he performed some of the experiments that I'd done some 10 years ago. And he knew that they worked, but he added, I've not told any of my colleagues or friends, because even though I occupy quite a senior post in the scientific civil service, I still have a few years to go to retirement, and I still cherish hopes of further promotion. That is a hell of a thing to say in the scientific world, isn't it? This man dare not tell his colleagues. We talk about blackbirds pecking out the white feathers of their colleagues or killing them if they can't because they didn't conform. This man is afraid of being put away because he wouldn't conform. Now this is not the time or place to go into the mathematics of the gyros. This I can do also. It is not the place to attempt an explanation of the phenomenon, but I cannot send you away hungry, you who have come to listen and to learn. I'm going to go back to an electrical experiment. In this theatre, someone said, Mr. Faraday, what use is all this? And he was my personal hero. He was the man who showed that Ohm's law was only all right for DC. I'm using this coil again. You put DC through it from a battery, and you get 4 amps and 8 volts. that coil has a property all its own, which we call resistance, Ohm's law. And with 8 volts and 4 amps, you get 2 ohms. Now we'll apply some alternating current to the same coil, and we'll get our same 4 amps. You got the wrong scale on, Manny. And you got the scale right. We're not cheating. You can try this yourself. This is obviously well known. The voltage is in fact 32. So now we have 4 amps and 32 volts, and we have apparently 8 ohms. We call them ohms, but they're not in Ohm's law. Ohm's law can't have 2 different values at the same time. The interesting thing is that over 140 years later, we don't say that Ohm's law was wrong. We simply say it is restricted to the use of DC.
Here we go. Check this out.
So, however distasteful it is,
check this out. This is good.
We now have to say that object has got something more than a mass. It's got a mass, so long as, and a mass only, so long as we want to push it about in straight lines, weigh it, accelerate it, so on. But if we ever choose to spin it, it has another property, all of its own, which corresponds to the inductance of a coil. This is the updating of Newton's laws of motion. But I'm not saying that Newton's laws of motion are wrong. I'm merely pointing out they are restricted to motion in straight lines and to motion where there is no rate of change of acceleration, just as there was no rate of change of current for Ohm's law. So that is at least some food for you to think about and some indication that I have.
So there you go, there's Eric Laithwaite updating the Newton's laws of motion, and you can imagine that got him into a lot of trouble. Well, you don't have to imagine it, it really did get him into a load of trouble. What I thought was really fascinating about that clip when I saw it relatively recently was he's saying there's a correspondence between the rate of spin and the number of coils, number of turns in a coil. So there's some correspondence he's observed, and he believed he could model mathematically between the spin of an object and the inductance on a coil, which I think is an incredible observation. And he was saying Newton's laws of motion work except when things spin. And as we know, lots and lots and lots and lots and lots of things spin. And in Newtonian mechanics, there's no explanation for that. So you can imagine what he said was quite controversial. He actually was booked to do this TV performance at Christmas in the 70s, and there was all kinds of controversy about what he'd actually be allowed to put on. He burnt a lot of bridges, I think, in terms of his career by saying, no, this is what I'm going to do. I'm going to show children this. And he was talking, as you saw, about the updating of Newton's laws of motion. Now, according to Frank James, Laithwaite after this, or not long after this, lost it. And he was saying how very sad it was that all of Laithwaite's stuff had been, or let's say none of Laithwaite's work that he did in conjunction with the Royal Institution was on their website. And Frank James and a few other people worked, I think, over a few years to get Laithwaite's work now, which is now included on the Royal Institution website. And if anyone wants to thank Frank James and tell him, or show him some gratitude, I think it's in order, and I'm going to share his email with anyone who wants to just say, dear Professor James, love what you did with, really appreciate the fact you worked on behalf of Eric Laithwaite's reputation, because now Eric Laithwaite is at least allowed to be spoken of in the Royal Institution. Now, what he actually did to get himself properly banned was something that I learnt about when I was a child, and it's one of my ways into questioning the laws of physics, because it's all very well talking about things theoretically. When you see what, if you haven't seen this before, what Eric Laithwaite does with a massive gyroscope, it is completely inexplicable in terms of standard mechanics. And this demonstration, showing people this, was really what got Eric Laithwaite into a lot of trouble. He got invited to the Royal Institution. He showed them this video, or this experiment we're about to show you, and they couldn't cope with it. It exceeded their imagination. Some people accused him of fraud or a conjuring trick, anything to prevent them from actually having to address this incredible correspondence correspondence he thought he found between the rate of spin and the cause in an inductance, the number of turns in an inductance coil. Thank you, Phil. Check this out.
This is an experiment with a spinning wheel, a rather large wheel, 13 inches diameter, mounted in a ball bearing on a shaft 3 feet long. I'm going to hold it like this and swing it in a circle and lift it with one hand, but only when it's spinning. First of all, let me weigh it to show you just how heavy it is. As I talk, you'll see that lifting it is quite an effort. It weighs about 40 pounds, and I can't lift it any higher than that without a lot of strain. So now we'll spin it up to 2,500 revs a minute, at which point it becomes a live thing. Then I shall lift it 5 feet in 3 seconds by going round in a big circle. Whilst I'm doing it, I shall talk to you so that you shall tell from my voice that I'm not under any stress of any kind. And the minute I shall let go with my left hand, and holding this remote end of the shaft only, I shall lift the wheel through 5 feet, all on its own with no effort on my part. All I do is apparently just to steer it along a path that it's already decided it would like to go.
You can pause it any time from here.
Then there's the question of...
So there you go. There's Eric Laithwaite breaking the laws of physics in public, getting himself into all kinds of trouble. Now, as discussed, Professor James has done a lot of work within the Royal Institution to get Eric Laithwaite's work and the footage they have of him onto the Royal Institution website, and that is now available. So there is a possibility that Laithwaite's reputation is a bit on the mend. Now, I mentioned ages ago that I gave Professor Frank James a gift. As discussed, we were just talking about Laithwaite, talking about physics in general, and I love these things. They're a great toy, and they're a great way of opening a conversation with people who have an interest in science. And all I'm going to do is I'm going to show you this toy in the spirit of experimental science. I've got this wooden top, and this is an example of what I gave to Frank James. So these are actually a bit tricky, and it skids about a bit, but the idea is what you'll see, if I can spin it correctly, is that the top will invert. No, that one didn't work. Hang on.
Why do it on the floor?
Because now hopefully people can see that.
Yeah.
The top has actually inverted. All the mass has risen, and on top, literally as I showed Frank James this, and it flipped, he stood up and said, "I need to go to the toilet." He went off, came back and said, "I'm going now," shook me by the hand, shook Piers by the hand, picked the tip top up without mentioning it, and it obviously invoked a reaction in him. Because I think it's a great toy. They cost like $1 or $2. These are made in the States by a physics professor. You can get them online, but for demonstrating the power of spin and the limitations of the Newtonian cosmology, I think that's incredible value for money. And it did got this amazing reaction from, like I say, Professor James. The moment I managed to make it flip, he stood up, said, "I'm going to the loo," came back, shook our hands and left. So one more time.
I was going to say, you probably didn't see that, did you, Jeremy? Because it wouldn't have been on the camera. No. So let's see if we can get this on the camera. Can you bring that over?
Oh, yes.
For the camera.
That was a good... You're missing out on a treat. Hang on, let me see if I can share this with you, Jeremy.
Yeah.
So, how do I know whether he's seeing?
There's the camera.
Yeah, I can see.
Okay, can you hold the tray for me? So, little wooden top. Can you see it's flipped?
Yeah.
It's just a wonderful. I'll send you one. They're $1 or $2. They're wonderful fun, and it was a really interesting reaction. He left, shook us. Looked us in the eye, shook us by the hand, and took the tip top and put it in his pocket. And that's my prediction is, having given him this little bit of wood that breaks the laws of physics, he'll never want to talk to me again. And so I don't know.
Well, I'd like to ask what Jeremy thinks of the fact that mass, once it's spinning, will actually defy the laws of gravity. This is something we talk about a bit, and we're all thinking about whether. Well, I'm thinking whether if you're spinning fast, you're shaking off electrons, and so does that counteract the laws of gravity? What do you think?
I'm not sure the details of this one. I mean, basically, I personally, if I was looking at one of these problems, would delve into it mathematically and would just, for those that know what
that's your next assignment
then. I'd be using Lagrange's equations to solve the spinning top.
So, could you say that again? I'm sorry, I missed that. The what equations?
Spinning top. And yet they're predictable by using Lagrange's equations to examine the motion.
Lagrange. So, what do you think of this ability for? I mean, it was very. You got Eric Lathwaite holding this 40-pound weight above his head because it's spinning.
Yeah.
What would Lagrange say about that?
I mean, it's amazing to see if you think about the weight of it.
Yeah.
But as far as the mathematics of it is concerned, I haven't gone into it, so I wouldn't like to say.
Do you have any speculation about the universality of spin? Because again, in this sort of Newtonian mechanics, there isn't really any account taken of spin, and we see it obviously everywhere. We see spin is a universal property.
If you look at the problem of a spinning top, you can write down the kinetic energy of a spinning top. You can write down the potential energy, and from those you can make deductions depending on the initial conditions. So I'm hedging on this because I wouldn't like to make a definite statement until I've really delved into it. And I would you can get a lot of surprising results by looking at the spinning top, looking at the mathematics of it. And there is something online somewhere that I've seen, but I haven't really delved into it, where somebody is claiming to have solved the mathematical model of Eric Lathwaite's demonstration at the Royal Society, at the Society.
Yeah.
Now, whether that's true or not, I honestly don't know, but I have read that it has been done.
I read...
And it's on the basis of Newtonian mechanics, basically.
Yeah, I read in 1990 some part of NATO, I think. Hang on, I've got it written down, sorry. Confirmed that what he was saying was accurate, and that they'd done, either experimentally or theoretically, they'd come up. Let me just get the right reference. I'm trying to remember who these people are. There's some acronym. The NATO.
Certainly, a lot of things, Robert, have come out from NASA.
Yeah, this is
which
the NATO advisory.
Finding that NASA is using ideas that are regarded as being a bit dubious elsewhere.
Yeah. In March 1990, apparently, the NATO Advisory Group for Aerospace Research and Development, AGARD, nice acronym, confirmed that they'd looked into Lathwaite's research and said that it was essentially sound. That was in a book by a man called Nick Cook, who I'm not always sure is the greatest source of information, but according to him and his sources, NATO actually confirmed in their aerospace research and development branch, confirmed that what Lathwaite was doing was legitimate. Of course, you never really get to hear about that. I mean, there is one little bit of video I've got of Lathwaite talking about the whole everything being spin, like, atoms spinning, planets spinning, stars spinning. And he had this, I'm going to say, spinning or spin-based cosmology that I just wondered if you had any...
Well, it's what something's got to make the spin, so that's got to be down to charge, moving charge, because you got to for work to happen. There's got to be some sort of input.
Yeah,
and that could well be the case. I mean, what you've got to remember, of course, about Lathwaite is one way he was lucky. If he'd been unlucky, he'd have done the demonstration for nature, and Maddox would have had him investigated by somebody from the Magic Circle.
Yeah, well, that might have worked. I mean, it wasn't a trick, was it?
No.
So we've got this upward force that the actual spinning gyro wants to take.
Spinning, yeah.
So why does it want to take that upward momentum? Why would a spinning gyro want to go up above his head? Why wouldn't it want to go down equally? Why does it, because it's spinning, which is up, down and everything, but it naturally wants to go up. It doesn't naturally want to go down.
I've seen an interview with a research engineer, I think for Lockheed Martin, who was talking about when you charge certain things, they lose mass.
That's right.
And I can't help but feel, in some sense, the spin is displacing.
That's what I'm talking about, throwing off electrons.
Yeah. Well, I wouldn't. I'm going with.
Well, in some way, the spin must be counteracting gravity.
Yeah.
It's very easy for you to come up with a mathematical model of this, or use the model of the spinning top to explain it.
Yeah.
But that only explains it mathematically. Once again, what is the actual physical manifestation that we're seeing here?
Yeah.
And I haven't got a clue.
No, it's one that we talk about quite often, and it's really quite fascinating to actually think of an electrical explanation as to why this happens, because it is defying gravity. Like I say, if you held it up there, it's not going to spin down to the ground. It only wants to go up. It only wants to go up.
Again, we're looking at gravity as being this major force, the sort of the crucial force that we have to think about. If you go, as I said before, if you go back to the 1800s, they weren't looking at gravity, they were looking at electromagnetism.
Yeah, absolutely.
Now here you've got the spin coming in, you've got your electromagnetic forces. It does seem to me that we know that in small areas, the electromagnetic force is 39 orders of magnitude stronger than gravity. Absolutely. For a start.
Massive.
Now, aren't we missing something by concentrating on gravity all the time?
Well, gravity's our starting point, isn't it? That's, we are stuck to a ball of rock, and it's our starting point. Sorry, it's just something's falling apart here. Come on. Yes, it's our starting point.
It's our starting point. As far as our everyday life is concerned, it is. But should it be the starting point for a research scientist?
Probably not.
Well, so what? I mean, for me, it just seems that this the treatment Lathwaite got was pretty brutal. He was pretty much he had his reputation ruined. He was ostracised deliberately, blackballed. I know is the sort of slightly was a phrase that gets used. There was a mark put against his name, and he spent the last 15 years of his life pretty clear that he'd been done over. And
yes.
What is it about? I mean,
in the 1990s.
Sorry, yeah. Just for me, his the fact he stated in the 70s that there's a correspondence between the rate of spin and the inductance of a coil just seems to me that, and I know he was working on some form of propulsion, and I don't know whether that's got anything to do with it, but it does seem to me that once people have stepped outside certain, laid down guidelines, even a man of his reputation, I mean, let alone, there's a man who was on national TV regularly as a well-known face, probably the best-known engineer in the country, completely destroyed it. It's amazing to me the power of conservatism, and I can't believe it's just ignorance. I can't believe it's just inertia. I have to think that in some sense, knowledge is being controlled. The cosmology we have is being defined by what is and what isn't allowed to be possible, what isn't allowed to be spoken about.
So are we getting now to the point where we're getting past this? Are we now at this point in history where we have the technology where we can openly talk around the world and question assumptions, which is all they are really, is mainstream assumptions. So are we now going to finally see this break and a return to proper science and to what we had back in the 1890s before the times of Bohr and Einstein? And
I was going to say again, I remember what you saying about, Jeremy, you saying about Tesla and what he did, almost necessitating some kind of greater command and control of the scientific process, because otherwise you had potentially everyone having a seemingly inexhaustible amount of energy, and that could lead to all kinds of anarchy. You can see it.
Well, I think to the point. You see, I don't agree with you, Robert, that it's conservatism that's.
Well, it's a word. It's a word. I don't mean it politically. I just mean it socially.
No, I didn't mean that. I didn't mean it politically either.
Sorry, what
because
do you mean?
I don't think it is the conservative view of people. But when you come on to something like Tesla, you begin to wonder what powers have been operating to prevent us from knowing just what he did and did not do.
Yeah, absolutely.
But what was it political? What was it financial?
It was both of those, I would have thought.
But you see, we're talking about political in the sense of power to the central government, regardless of what politics that government may have. To a certain extent. I mean, there are all these rumours about Tesla, who was behind him. Somebody has sent me a book about Tesla, but he sent it on, I can't find it in hardback, and so I've got it on the computer, and I don't find it very convenient to read too much on the computer. But various big names with which we're all familiar, the families of which are all wrapped up with the so-called Bilderberg group and so on, they're all listed as having this big financial interest to shut Tesla up. Now, is there any truth in that? I don't know. You're just left wondering with things like that. Then with Laithwaite as well. Why was Laithwaite destroyed in order to silence him?
And why was you quietened as well?
Well, I think I'm a minnow compared with them.
Yeah, but I mean, at this point in history, you are, with the fact you was quietened and the fact you've been asked back to referee, you are one of these turning points. However modest you may like to feel about yourself, just happen to yourself, find yourself in this position, which is really, really good, I think.
Well, I do, but I mean, it's purely by accident. But I mean, when you look at people like Laithwaite and Tesla, look, we're talking about a different league.
Oh, absolutely.
Yeah,
nothing against you, but I do know what you. We know what you're saying. Yeah,
it's these different instances
coming together.
These different examples of a similar process. I mean, with conservatism, I guess that is a slightly loaded term. You could call it sort of orthodoxy or inertia, but I know there are lots of electric vehicles in the early 20th century. Tesla made an electric car. It doesn't take a genius to realise that oil is a big business, and that obviously if everyone was able to run things and even generate free electricity, there'd be an awful lot of people left out of pocket. And these are people who have driven, I mean, in our modern times, only a willfully naive person would say Iraq wasn't about oil, for example. These are the forces that move history along. So one man like Tesla, I don't think stood much of a chance,
No, in the past, individuals didn't, but this is what's very different about this day and age, is the fact that we can sit around and talk about this and discuss it openly, and the world can listen if they wish, and take different views on it. We are literally living in a very, very different time. Yes, and I'm just looking at my watch, and we've just got a couple of minutes. So I would like Jeremy just to give his final couple of thoughts as our special guest on where we're going to be going next year, and then I think we got a little, something's coming from Piers. He couldn't make it tonight. He has sent a message through asking us to say something.
Okay.
So I'll let Sharon say that first of all. What's this announcement from Piers?
Yeah, Piers is just saying that, they've done a bit of leafleting, and the leaflet's on Weather Action on Piers' website if you want to have a look at it. And he was also on George Galloway's talk show, so you might want to try and have a listen to that if you can via the webinar. And yes, he is having a public meeting on the 20th of December. He'll let you know where, but you can go to his Facebook page, or you can go to the weatheraction.com page as well. Thank you.
Excellent, fantastic. Cheers, Sharon, and thank you, Piers, for that update, even though it was via the phone rather than in person. But we'll forgive you that this time. And yes, so Jeremy, so where do you think we are going to be going in 2019? It could be a very exciting year with all the bits and pieces we've got going and have planned.
Well, although some people may not agree with me, I'm not Mystic Meg.
We have proof to the contrary.
I'll say what I hope would happen.
Okay.
And I just hope that we're entering a period where we're going to be more open-minded to ideas across the board in science, not just physics, across the board. Let's listen to people, evaluate what they've got to say fairly, disagree with them by all means, push them to give more concrete proof of what they're asserting by all means, but let's listen openly and not close down avenues of research just because they could lead to results which could be inconvenient for the careers of some people in very high places.
Well said, sir. Yeah. Absolutely.
Yeah.
Well, Bob, you to wrap up. We've literally got a minute.
All right. I just wanted again to say thank you to Jeremy. It's been really kind of you. Thank you for sharing your experience. Again, I just think, if I may say so, what you experienced and how you dealt with it is kind of a good role model for us, for people in the community, because you stuck to your guns. As you said, you didn't waste time or energy getting angry about it. And you've been, to my mind, it seems you've had some serious vindication since you made that prediction. So I won't call you Mystic Meg, but may I call you... I don't know.
Marvellous Mike.
If that works. Jocular Jerry. I don't know. I can't kind of think of something alliterative.
We'll think of something to
I'll think of something and I'll text it to you, but hopefully it'll be witty by then. But it's just been really kind of you to share your time. Thank you so much. And I hope to see you again when you come down to London.
Thank you very much. And just one last point.
Please.
My nickname, because of my surname, my nickname when I was an undergraduate was Dee. Yeah. So you can call me Dynamic Dee. Okay,
that's a strange request to finish on, but probably not inappropriate. Thank you so much, Dee. That's all we need now is a safe word. All we need now is a safe word, isn't it? So we'll be fine. All right. Well, please take care of yourself. Thank you so much.
Okay, well, we're going to stop the broadcast now on Facebook, and we'd like to thank you all for popping along, and and even if you're watching the recorded one. So see you later.
Thank you.